Hello, everyone. My name is Mike Lopez, and today I'm going to be talking about predicting, there we go, rates of recombination in the Maize genome. Let's see if I can figure out the lights. Ooh. Oh, that's too dark. Oh, there we go. Okay. Wait, no, there we go. Okay, we got it. Now we can start. All right. So, in a world with an ever-changing population, always growing, we have to make crops that are highly adaptable to the environment, similar to this crop right here growing on the side of the road. And we also have to make crops that produce very high yield because with very large population, we need more crops to feed those people. And the goal of many plant breeding programs across the country is to take these crops with really great adaptability or really great traits and breed them with other great crops that have other great traits, with hopefully the goal being minimizing deleterious traits, things that we don't really want to expect. Having googly eyes on your corn, don't want that. So one of the main driving factors of this is recombination. And what recombination is where you have two homologous chromosomes and their arms start to interlink and it's exchanging in a crossover event. And after that crossover event, we now have those deleterious, or we have those alleles cross over with each other onto one other chromosome arm. And the main reason we focus on recombination is because this is the way that positive alleles, which are closely linked to deleterious alleles in the genome, can be broken through crossing over. This is the way that we found breaks those alleles. And so the overall goal that we're aiming for is that by using machine learning, a machine learning model trained on a genomic and epigenetic data set, we can predict recombination rate throughout the Maize genome. And so there's probably a question on your mind. What is machine learning? It's a big, big topic. And I think a great way to explain it would be using the Wordle. I don't know if you guys have used the Wordle. I know some of you over here have used the Wordle. But I think a way to explain it would be that, say we took our input data set or have a starting data set of every 5-letter word in the English dictionary. And the goal is in Wordle is to get ultimately with 6 guesses to an all green state where we guess the correct word or guess the correct word. And so let's start with our first guess. We have stare. Now, if you played Wordle before, you know this isn't right. You know you're getting some hints, but not close to the right answer. So what we know from here is the feedback colors. We have feedback colors of gray and yellow. Gray being that we have the incorrect letter. We shouldn't guess that again. And then yellow being the correct letter in the incorrect position. So we know to take these and improve the accuracy of our model, or me just guessing. And we could do this over and over again to where we optimize our guess. And if we do this again, now we have radio. And that's a new guess. This time we have a new box, a green box. And this means we have the correct letter in the correct position. And so what we're going to do is take this input and put it into our next guess. And we're going to do this over and over again to where now we have a better guess. And sometimes whenever you make changes, they are always going to be better, but they help you make better options for your next guess. For example, from this guess and this guess, even though the green boxes are the same, we now are moving possibilities of M and Y and L and B. So we know to update our next guess. And eventually, through this over and over again, you get to an answer that you like. For example, all green favor. And so how are we going to use machine learning in our model to predict recombination rate? Well, we're going to use a subset of machine learning called supervised learning, where I will train the machine and help it make decisions that should aim towards something that we're looking for, aka predicting recombination rate. And that process uses something called regression. And regression, you may have heard of it in statistics, but it's basically where you take a known sample or a known subset and use that to predict unknown samples within that subset, or that could be within that subset. And so I think a good way to explain it is to take this example where we have 5 samples, 3 known, 2 unknown. And if we see the patterns of the first 2 samples, we can see that 1.5 and 2.5 are our known samples. And can't really make much patterns from here, but we do know if we use a little bit of algebra, a little bit of math, that we have a slope of 1. And if we use that as our sole predictor, we can predict an unknown value being next of 3.5. And if we follow this pattern, assuming it's correct, we now have 4.5. And how do we know this is correct? We take this other known sample, which we separated from our first 2 known samples, and test it. And we'll see how accurate we are. So 5.5. That's great. It followed the pattern and we got a good accuracy. That's always the goal, trying to make sure the known values are used as training and testing. And then we use that to predict our unknown values, hopefully making one smooth, accurate prediction. And so for my model, what we're going to try to predict, and this next slide is going to be scary, is recombination rate. This is the estimated recombination rate that we found in the Maize genome of what we believe to be like the goal we're aiming for. And this was found using a subset of features. And those features, well, I'll feature them on the next slide right here. We have about 3 subset of features in our data set. We have DNA sequence features, which are features determined by the DNA sequence itself. We have histone modification features, which are into 2 different subsets. We have methylation features and acetylation features. And if you've never heard of histone modification, it's a type of epigenetic modification, particularly affecting the histones on nucleosomes. And then we have a different subset of features known as methylation, DNA methylation, I should be specific, features. We have MCG, MCHG, and MCHH. And what methylation is, it's a small little modification on the cytosines within our genome. And so these 3 subsets of features will help us determine, or at least were determined in the paper to be the most accurate way of predicting recombination rate. And so let's look at a small example of this to make sure that our data is good enough to predict all the lows and all the highs. So we're going to take the top 2% and the bottom 2% of MCG within our data set and see that not only can we see all the variation in between the top and bottom 2%, but with our model, it's because of this variation that we can predict everything in between. Or maybe even use this to detect patterns and predict things outside of this range or outside of this range. And that's the hope with us. And we're going to be using multiple of these models. Like right now, this is just MCG. We can also use MCHG and see a similar model and see the patterns from that and derive predictions from there. But we do have 2 different data sets. We have a local and a global data set. And you may be asking, why do we need 2 different data sets? We already have a really big data set. Well, the local data set is about 10 kilobase intervals. And those are more high resolution for predicting crossover hotspot recombination rate. And the reason we want that is because we want to look at which specific alleles can recombine at which rate. And so by finding the recombination rate at crossover hotspots alone, it'll give us a great example of that. And here is just showing what the local methylation pattern looks like at the local level of 10 kilobases. And then we have a global recombination pattern, which gives us a more accurate overall average of what the genome recombination rate would look like without going too large to where we don't have enough data to train our machine learning model. And then here we have the global methylation patterns, which the mean for the CHH pattern is the same. However, these small differences between the means of the CHG and CG patterns can make all the difference when it comes to predicting an accurate model or estimation. And right now, these resolutions are just unknown, these resolutions are best for predicting recombination rate when it's unknown. And what that means is that we don't know yet the right resolution to look at to get perfect recombination rates. That's why we're taking what we believe to be the smallest sample we can do and the largest sample we can do while still having enough data to train our model. And one thing that's important about training models is making it very, very accurate. So how are we make our model accurate? We're going to use something called XGBoost. And what that does is it optimizes models using decision trees, and it optimizes it for high accuracy. So let's talk about what decision trees are. Decision trees is where you take all of your data, put it into a subset, and put it into a tree. And this tree shows you all your possible options, every feature laid out. But a tree is very easy for taking apart data and putting it into different ways, different configurations. So for example, on the left side, if we want to if we want to have less features on the right side of our tree, we can take those away, see what our accuracy does, see if it changes, see if it lowers, see what changes happen. And then we can do that for the same side over here, except we take less features on the left side of the tree. And these different configurations can affect our accuracy in major ways. And it's all about using every type of configuration we can find. And so after doing this with XGBoost, we found that the features with the most importance, where if we take some away, it drops the rate below, or drops recombination rate prediction very, very low, or its accuracy very low. And we found that for high resolution, that methylation patterns, histone patterns, and also DNA patterns were very, very important, as we expected, with the highest feature important being CHG methylation in specific. Then for our low resolution, we found that it was also methylation patterns, histone patterns, and SNP density as well, going up one more rank in there. And we found in this one that the feature with the most importance in determining or predicting recombination rate was CG methylation. So as you can see, there are differences when it comes to these high resolution and low resolution data sets. And maybe somewhere in the middle, we can find a good we could find good features to predict everything. And so let's look at the accuracy in our predictions. We have the low resolution data set, we have the high resolution data set. In a model that's non-optimized, or as known as the default model, we have a 46% accuracy with an error offset of 0.0478, which means that's how off our accurate predictions were from the actual value. Then we have 56% we have a 56% accuracy in our high resolution default model with a error offset of 0.0017. So great error offset, but not great accuracy. Now, if we optimize this, we now have a better, but not great accuracy of 67% on the low resolution at 0.0015 offset. And then we have 85% optimized accuracy with an error rate of 0.0078. And 85%, that's really good. That's great. However, we can make it better. And we can make 67% better too. But how will we make this better? Well, that leads into our future directions. Before, we used trees to predict our accuracy, and that was pretty accurate for the high resolution model. But to make it more accurate for our low resolution models, we're going to use something called a recurrent neural net. And if you don't know what that is, I'll explain it. We have A, which is our input, and we put it through our model or put it through an accurate model. For example, we can put it through something like XGBoost, and it gives us a hidden layer of B. And through that hidden layer, we can see what changes were made to increase that accuracy. And we can do that over and over and over again, maybe even hundreds or thousands of times. Even if it slowly increases the accuracy, it's still increasing it, and does it until it can't increase accuracy anymore. And once we have that highest accuracy output model, we can then have C, which is our final output, which is the most optimized model that this recurrent neural net can come up with. And so some conclusions we can draw from this is that we've reached an accuracy of 85% on the high resolution model using XGBoost optimized for machine learning. And we found that in the high resolution model, the features with the most importance were MCHG, histone modifications, which is these ones, and also SNP density, which is a DNA modification. Then we have the low resolution models, the features that were most important when it comes to predicting recombination rate, being MCG, more histone modifications, and then SNP density. And as you can see, there's something in the middle that combines these two, SNP density. That's going to tell us whenever we want to change our resolution from maybe higher 10 kb or lower than 100 kb, we know that SNP density will probably be one of the features that stays concurrent throughout that. I would like to thank everyone in my lab. It's my mentor, it's my PI. I also like to thank BTI, Cornell Biotech especially, and also NSF. Any questions? Dahlia.
Yes. So 1 second.
Sorry.
So that was really, really great. I don't know if you would know this, but something I'm curious about is, does your lab have any plans for I know a lot of machine learning, one of the hot topics these days is copyright and trademarking of different machine learning algorithms. Does your lab plan on making this open source yet? Do you know?
We actually use the open source algorithm XGBoost. That's already an open source algorithm. We use that one and just trained our model on top of it.
Okay, so everything is open to the public algorithm that you expect to be used by other labs in the future, hopefully?
Yes, hopefully. That'd be great. XGBoost is great for making machine learning models more accurate. And for our machine learning model, it was more just using regression. And that's also open source. A lot of our stuff is open source. And XGBoost is just one of the many open source things that we use.
Awesome, thank you.
Hi, thank you very much for your presentation. It was wonderful. I have a question on what we do with this data. So you're going through the Maize genome and figuring out, okay, this is what is predicted to be the recombination rates across this entire genome. And you had mentioned at the beginning about plant breeding. I was curious, how is this data useful to a plant breeder? So how does a plant breeder take this data of the recombination rates, and how do they use that to better crops?
So the specifics of that is not yet known. However, what we were hoping to do is take that inefficient process of plant breeding multiple generations over and over again, just to try to remove certain traits from certain crops. And in plant breeding, we hope to use the accuracies we found to predict where exactly these crossover spots are occurring and how exactly the crossover rate of certain alleles. For example, if we want a positive allele and not a negative allele, we can see what the rate of crossover is there and expect to see a good plant that we want, or a more elite population of plants that we want in a certain time frame with using that accuracy.
Thank you.
Yeah, we're out of time for questions.